Assalamu alaikum. It's our 12th lecture of Advanced Electromagnetic Field and Waves, and in this lecture we will discuss about the how we can write the electric field equations when we have non-planar plane coordinates. Okay, as you know that in previous some lectures we are doing to find the fields equations either for electric field or magnetic field, but in that case our plane is plane coordinates. But now in this lecture we are going to solve if our coordinate is not plane, means it electric field or your wave propagation makes some angle theta. Okay, some different angle. Okay, so how you can solve in that scenario? So this is first, there is a region. This is region 1. This is region 1, and beyond this line this is region 2. What you have to find the electric field equations. Okay, the wave is incident from this. Here you can see, this is the incident line, this. Okay, this is the incident electric field. How you can write the field equations, I will thoroughly brief you. Okay, so first of all, you have to know that this is the incident electric field. After striking the boundary it reflects back. This is the reflection back wave. Okay, and some of the wave after striking this boundary transmitted to the other medium. Okay, this other medium. Okay, so this are the incident making an angle theta I. This is the reflected electric field making an angle theta r. This is the transmitted electric wave making an angle theta t, denoted by theta t. Now how you can represent? Now you can see, this is the direction of electric field, ei. Okay, arrow. This is the direction of electric field, and the wave propagation is this, ki. Okay, arrow from this to this. So this is the direction of wave propagation, and this is the direction of electric field incident. To solve this, first of all you have to split into the coordinates. How you can split this into coordinates? You can easily split this. So first of all you must have to know that you have to make the coordinates makes perpendicular from these coordinates. As you know that these coordinates are this. This is one perpendicular coordinate, this is another z coordinate. You have to draw the similar coordinates on the origin point of this axis. Okay, so you can see this is my perpendicular component and this is my normal component. I draw on the origin of electric field and k wave propagation k. Now you have to drop your angles. So what you have to do, because your electric field into the x-axis and your wave propagation into the z-axis, so you have to drop your axis of electric field to the x-axis region. This is the line of x-axis. So you can see I simply drop my electric field lines to the x-axis. So from the base, so it making an angle theta I. Okay, so the direction from theta I to this is our base. As you know that base is the cos theta. So because this is the direction in positive x direction, because arrow is upside, so the base becomes x cos of theta. Similarly, from base it goes perpendicular. So perpendicular is upward, means this is your vertical part. Okay, this is your vertical part, and you know that vertical part is basically the sine theta part. And you can see here is the z direction, but in opposite direction it is going, because you can see arrow is this side onto this side, so it becomes minus z sine of theta. Okay, so this is the coordinate components of electric field. Similarly, you have to draw the components of wave propagation ki. Also you can see this is the wave propagation. Now you have to split this, but where you can drop the lines, because your wave propagation is in the z direction, so you can drop the lines along the z direction. Because so this is the z axis line, so you can see I drop my k to z axis after dropping, because this is now base. and this is going arrow this side, and from base arrows upside, so upside. So this is making an angle theta I. So in front of angle theta there is a vertical component, so and the vertical component sine theta I because incident, and this is in the direction of x, so it becomes positive x, sorry, x cap. Okay, and this is your base is in the positive z direction, as you can see here, so that's why it becomes z cos of theta I. Okay, because base is always cos theta component and perpendicular component is basically the sine theta component in front of theta. So these are the electric field and wave propagation components in the incident wave. Okay, similarly, when your wave strikes to the boundary, this is your boundary, and some of the wave is reflected back into the first medium and some of the wave is transmitted into the second region. Okay, so let's find once your wave is reflected back. As your wave is reflected back, now your direction of wave propagation, you can see it changes. This is into, now you can see this is wave propagation out. Okay, but the electric field direction is again in this direction. Okay, you can also take a downward direction, no issue, just you have to use all the aspects then along with that. Okay, so no problem if you make an electric field on this direction or either downside. Okay, no problem. But only the thing is the direction of wave propagation, this is, you can see outgoing, and in for the case of incident you can see this is inward. Okay, but here you can see this is outgoing and electric field upward. Now again you have, what you have to do, you have to draw this and this uh, coordinates along with the center point of wave propagation and electric field. You can see I draw this line and I draw this line. Okay, along the central point of electric field and the wave propagation. Okay, so after drawing that you have to split your resolution lines. So this is your electric field, so you know that electric field in the x-axis, so you have to drop your electric field along the x-axis. You can also drop down, but why you are not dropping down? Because this is the z-axis line, your electric field is in the x-axis, that's why I dropping my electric field coordinates into the x-axis. Understood? Okay, so that becomes perpendicular, and below is basically the base. Okay, below it becomes the base. Understood? And you know that base is basically the cos component, so it is cos and it's going in the positive x direction, so it becomes positive x cap cos theta r. Okay, because it's the reflected angle. And similarly this perpendicular part, and this is in front of theta, means this is vertical component, and vertical component basically the y component means sine theta, so this is sine theta r. Okay, and why z positive z direction? Because you can see that wave propagation of sine theta component is in the positive z direction. So this is how you can draw this thing. Okay, similarly, the wave propagation in the first region but reflected part is how you can find. Similarly, you can see this is your wave propagation k. Now you have to split the components. How you can split component? You have to drop your lines along the, because your wave propagation is in the z direction, so you have to drop on z axis. You cannot drop this on y axis line. Okay, so that's why we are dropping the k on to the z axis. Now this becomes the perpendicular part, means sine theta, and this is in the positive x direction, so that's why x cap sine theta r. And similarly base, but base you can see that this is in the negative z direction, because here is z direction but in this direction is the negative z direction, and this is base, so it becomes minus z cos of theta r. Okay, so this is the wave propagation components, and this is the electric field components in the first region for reflected part. Okay, now let's resolve for the case of transmitted part. Now this is your transmitted part. You can see your electric field in this direction and your wave is propagating in this direction. Okay, this is kt, and this is et, means electric field in transmitted, in second region transmitted part, and wave propagation in second region transmitted part. Okay, now along again you have to draw this coordinate and this coordinate on the central point of electric field and wave propagation. So this you can see I draw this and this plus sign. Okay, in the central region. Now what you have to do, you have to just again the split of lines, because you know that this is electric field and we have to drop lines along the x-axis line. This is the x-axis line, so you can see I drop a line, and this becomes base, and this becomes now the perpendicular component, and this is in the negative z direction, is going this, so that's why it's become minus z, and this is in front of theta, means this is a vertical component, so it becomes minus z sine of theta t. Okay, similarly this is base, and base is in positive x direction, so it becomes x cos of theta t. Okay, similarly you can split the components for the case of wave propagation in transmitted part. This is your wave propagation. Now you don't have allowed to drop this on the y-axis, on the x-axis line, because your wave propagation in the z-axis, so that's why we have to drop the wave propagation line on the z-axis line. So this is the z-axis line, so that's why I dropped this, and so this becomes base, arrow is this side, so it becomes minus positive z direction, and this is base, so it becomes cos of theta, means z cos of theta t, and this is in front of theta t, transmitted angle in front of it, which is the vertical component, and vertical component is the sine theta, so that's why it becomes sine theta, and this is sine theta is in the positive x direction, so it becomes x cap sine of theta t. So this is how you can resolve the components of electric field if your coordinates are not plane. Okay, there are two regions in this scenario: region 1, which contains incident wave, and which contains also the reflected wave, but in region 2 there is only the transmitted part. Okay, now you just have to write the field equations of this. So let's start for the case of first incident. Just let us just write the field equation of incident electric field. So here region 1, which contains incident part as well as reflected part, so region 1 is basically the sum of incident plus reflected. Okay, incident plus reflected. And similarly just first of all write the field equation for incident is this. Okay, how you can write? So you can see incident, so that's why it's denoted by ei. Okay, ei for the case of incident equals to e naught. E naught is basically the amplitude constant of this wave, and this is first of all you have to write the electric fields for coordinates of electric field, and these are the coordinates of electric field. What are our results? X cos of theta I minus z sine of theta I. Understood? So as similar we write x cos of theta I minus z sine of theta I. Okay, now exponential e power the components of uh, the components of the wave propagation. Okay, so how you can write this is the components of wave propagation. Understood? So e power becomes z, you can write from this x sine of theta I plus z cos of theta I. Similarly you can see x, okay, sine of theta I for this plus z cos of theta I. Okay, with k also, because you know that exponential power iota k x. Okay, that's why iota is also here, and k, because we are in the incident part, so it becomes ki. Okay, so iota ki x sine of theta I plus ki iota ki okay, z component, because this is z component cos of theta I. Okay, understood? Now similarly you have to write the uh, field equations for the reflected part. This is your reflected part, and first of all denoted by er, so er equals to e naught, which is the amplitude constant. Now you have to write the components of electric field. This is the components of electric field. What is this? You can see here x cos of theta r plus z sine of theta r. So simply we wrote here, you can see here x cos of theta r plus z sine of theta r. Similarly exponential power iota kx in general, but here we have to split, so that here we split it, so we have to initialize that e power iota, because we are in the reflected region, so it becomes kr. Okay, kr. Now what is the components of this? You can see here this is the components are this. x sine of theta r minus z cos of theta r. So you can see x sine of theta r minus z cos of theta r, k r with both because you are in the reflected wave, okay, in reflected wave, that's why k r, and iota is also with them, okay. Similarly, now move on towards the transmitted part. This is your transmitted part, okay. How you can write the transmitted part? So again, it denoted by et equals to e naught, which is the amplitude constant, and you have to write the electric field coordinates, and this is your electric field coordinates. And in this you can see x cos of theta t minus z sine of theta t. So you can see x cos of theta t minus z sine of theta t. Exponential power same, iota k x journal, but you, as you split it your component, so it becomes iota k, because you are in the transmitted part, so it becomes kt. And now the components of wave propagation is this, means z cos of theta t x sine of theta t. So you can see x sine of theta t plus z cos of theta t, and kt and iota also with them. So this is how you can write the electric field equations when your coordinates are not plane, okay. And when your coordinates are plane, we already have 2 to 3 lectures of that videos in our playlist. If you forgot to watch, you can watch those videos first, then move on to this lecture, okay. So that's all for today. If you have further any query related to this today's lecture, you can leave the comment below. I can definitely answer your questions. And if you have a detailed discussion, you can just drop your mail. I will contact you there, and you can easily discuss with me, okay. So that's all for the lecture number 12 of Advanced Electromagnetic Field and Waves, Electrodynamics, okay, in which we solve incident, reflected, and transmitted electric field waves, how we can write when our coordinates are not plane. We will upload more interesting lectures for this course, Electrodynamics. So for that, till then, take care and Allah Hafiz.